final thing I wanted to say right now about Euler's pentagonal number theorem is first to draw you this picture to show you where we get the pentagonal numbers. So it's just the trivial pentagon and then one pentagon nested inside another, nested inside, where we anchor this corner each time. And we're going to get the pentagonal numbers given here. Remember that when we expand this out, we did the folding argument over here, so we can expand that out to get us a nice positive sum. And what we found is that the product k greater than or equal to 1 of 1 minus x to the k, this is equal to 1 minus x squared. These terms all come in pairs, again, from the folding argument. And the first of each pair is going to be the pentagonal number. And then our gap is going to increase by 1 each time between successive coefficients. This can be minus x to the 12, minus x to the 15, plus x to the 22, plus x to the 26, and so on and so forth. Okay, so we saw that that actually gives us a recurrence relation. So let's go through that again. Remember that the partition generating function is what I'm going to multiply by. So the left-hand side is going to be the product, k greater than or equal to 1, of 1 minus x to the k times the product k greater than or equal to 1 of 1 over 1 minus x to the k. That's the partition generating function, and what we get is the sum n greater than or equal to 0 of p of n x to the n times, well, let's save ourselves a small amount of time. And now when we write this out, the point is that we're going to get this lovely identity, which is going to be p of 0 plus p of 1x plus p of 2 x squared times this guy. And we're going to have more terms, of course. And so if we think about taking the coefficient, so the coefficient of x to the n over here is 0. And now what is it over here? And we're going to get an identity. So if we want to get an x to the n, we could get a pn times 1, right? So we can get p of n. Or we could get p of n minus 1, and then we're going to need to pick up an x. So we're going to get minus p of n minus 1. We could take a p of n minus 2, but then we're going to need to pick up an x squared, p of n minus 2. And now we can't take p of n minus 3 because there's no x cubed. So the next term that we can take is the one that comes with the x to the 5. Okay, so that's going to say positive sign, so we're going to get p of n minus 5 plus p of n minus 7 minus p of n minus 12 minus p of n minus 15, and so on. So again, we're taking each one of these terms. The 1 gives us the pn, the x and the x squared give us these two terms, and then we can take these guys, and so on and so forth. So we get a recurrence, and it's finitely many terms, right? So when we wrote that down, for example, for, let's do it in example color. When we write that down for p of 20, what does it come out to? And so again, I want to pull the pn and move everything to the other side, so it's going to toggle my sign. So I get p of 19 plus p of 18 minus p of 15 minus p of 13 plus p of 8 plus p of 5. And now I'm done, because now I'm going to be subtracting 22 from 20, and you can't do that. And so if I compute these numbers, I think, whoa, okay, let's not do that. If I compute these numbers, I get 490, 385, 176. And of course, each of these can be computed by its own recurrence. So that's the nature of recurrences. They are recursive. But it's not a bad way to find out there's 627 partitions of 20. And I think it's important to notice, like, how good is this? How many terms do we have? So roughly, and it's not too hard to do that analytics on this, and I'll leave it as an exercise. Roughly, we're going to get 2 times the square root of 2n over 3 terms in the expansion. So let's just check that for n equals 20. So we're going to get 2 square root of 40 over 3. And again, because we're doing approximations, let's say 40 divided by 3 is 13. So we get 2 times the square root of 13. 13 is roughly 9. So we get 2 times the square root of 9, which is 6 terms. And if we count the terms, 1, 2, 3, 4, 5, 6. So it's a very good estimate. And another thing, just the last thing to say, since we're at the very bottom of the page, but maybe I'll put this in red, is you can use Euler's Pentagonal number theorem to do an estimate of the actual growth of the partition numbers. So I'm not going to put a proof of this in there, but it's something that I can give you a reference to if you want to see it. But roughly, the partitions grow like an exponential with a square root, and you might notice, that's not a pi, that's an n. It's not a constant. There we go. 2n over 3, sorry, 2n over 2 would be rather stupid. 4 square root of 3 n. I'm going to emphasize the square root's not in the bottom. So this is roughly the growth of the partitions. So they're exponential, but not quite, is a good way to think about it. And again, this all comes out of analyzing the Euler's Pentagonal number theorem. It comes from doing these sorts of applications where we get this lovely recurrence that we can actually get from this. So it's a really powerful tool. The proof itself, I think, is lovely, and it comes with some nice elementary combinatorics